Hello, everybody. I'm very excited to be here because I believe that news is the future of stock market prediction. I remember when I just started doing that, I had many scientific lives, and one of them is this one, stock market prediction. I was analyzing stock data, and my wife said, "How can you predict the market if the news could come about an earthquake?" I said, "You're right." And then I found out that nobody was normalizing that, and I had to analyze the text myself, which was kind of forget it. So for many years I was doing high-frequency trading where you don't need to analyze the news, hopefully, because it is already processed by the traders. But I kept thinking about that problem, and fortunately now we have the news normalized, and I believe that's a great source of information, and that's the future of the trading. So let me proceed with my talk. So the most important thing here is correct mathematical definition of what is mutual information, because that's such a which one? This here. Oh, okay. Because mutual information is such a catchy word, and many people misuse it. And there is correct mathematical definition, and that really matters here. So the relevance of the mutual information comes from the fact that there is mostly random walk on the Wall Street, but there are also fat tails. And fat tails is really where all the gems of this pile of dung are hidden. And if you just use traditional analysis like correlation analysis, you would mostly get stuck in the dung, and those gems would be averaged to zero. So it's important to use mutual information which doesn't have that flow, and that's my point. And then you could correctly discretize this abstract definition of mutual information, and that provides you with something which detects those gems. And then I will talk about specific subject of today's conference, which is the news signals from RavenPack and how they are related to price movement. And then I will present you some results. First of all, there was some formula for mutual information of continuous signals, and this formula is important. So let's consider there are two variables, random variables, with certain distribution, like P1 and P2, and one variable could be the delta price on the previous moment, or it could be some volume disbalance, or it could be the normalized RavenPack indicator at some moment, and x2 would be the subsequent price move from that moment till the end of the day. That's an example which I'm really interested in, but from the mathematical point of view, it could be anything. And here is P12, which is their common PDF. Common PDF means that you measure frequency of their simultaneous occurrence of these events, as opposed to P1 and P2, which were individual appearance. So when in the time series event 1 appears with some frequency P1, event 2 appears with some frequency P2, and P12 is frequency of their simultaneous appearance. So the definition of mutual information is integral, double integral over distribution of both of these variables. That's this common PDF. And this is the ratio of this same common PDF to products of individual PDFs. And the key is that this ratio has very nice mathematical property, and that's what we're going to discuss in a minute. And that is something often overlooked in practical application. Now, we use logarithm-based 2 just to analyze it in terms of number of bits. It doesn't really matter. We could use natural logarithm, as many people do. Now, the important thing which I just mentioned is parametric invariance, and that's really the key. You could change variables. You could change your signal to any function of this signal as long as this function has positive derivative. In other words, you could change x to the x to 11th power, or x to the hyperbolic sine of x, or x through something hyperbolic tangent of x. As long as the derivative is positive, that's called diffeomorphisms, you would not really change the mutual information. Believe it or not, that function, that value, that number, doesn't really depend on how you define your signal, as long as you redefine it in monotonous way with positive derivative. And why is that important? Because if x has a Gaussian distribution with huge maximum at 0 and very, very small tails, then x to the 11th power has much bigger tails. So if you raise your signal to 11th power, then you would clearly punctuate the tails and the information would not change. So it really measures what is important in your system. And that's the curse of the analysis of the market data, because 99% of the time the random walk is correct. It is huge Gaussian distribution, and only the tails are interesting. So mutual information knows about that. So the PDF, the mathematical proof of that invariance is very simple. You just see how the PDF transforms and see that indeed the mutual information stays invariant. And that's why it doesn't lose the tails, as I just said. And that's what I already told you, that fat tails will be visible in this mutual information as long as you preserve this parametric invariance. Unlike the Pearson correlation, which is not. In case of important signals, Pearson correlation could be very close to 0, and that's because the tails play a very small role in Pearson correlation. But mutual information doesn't tell you how to use it, but it tells you what you can get if you properly threshold the signals. So it is not the practical recipe to use. I will keep those to myself in this talk, but it is something which you have to keep in mind. It tells you how much you can extract from this signal if you want to use it, if you use it properly. Now, usually when you replace sums, integrals by sums, you lose all the nice property. Not here. There is a way to discretize this definition of mutual information without losing parametric invariance. And that's extremely important in my view. Simply, if you use bins, not in the variable x, but in probability. In other words, you use quantiles. You use the bins which have equal amount of probability in them. And those bins, if you replace the integral by sum over those equal probability bins, then you still have the parametric invariance. Why? Because what is probability bins? You have your variable, you sort all data in your possession, and then you just mark the certain points. In other words, you rank the data, and you just, for every data point, you have the fraction of the data before you. Now, if you raise your signal to the 11th power, they will be sorted all the same. The sorting doesn't change when you make those diffeomorphisms. So that's why those bins will not be correct formula for the integral, of course. Only in the limit of infinite number of bins you get correct formula. But your approximation would still not lose parametric invariance. And that's why this important property of not losing tails will still be there. Of course, the normalization of bins is such that they're normalized to 1. That's the definition of probability. So even with small number of bins, you preserve invariance. Then there are some practical ways of measuring that, doing that, and approximating it to an infinite number of events would be to use so-called bagging. Bagging is you just repeat your statistical analysis many times. Instead of original set, you just draw events out of original set with some probability and use it's called bag, and you repeat it many times and average over bags, And surprisingly, that improves your statistics, because each bag statistically is equivalent to the original system, and they're different. So you add many possible representations of your system, and that reduces noise. That's why bagging is relevant to computation of mutual information. So let's describe now practical ways of using that. Suppose you will consider a logarithm of the price ratio of price of next day close to the one at the moment of the news. The price at the moment of the news, of course, is not price before the news. It's the average price of next minute after release of the news. Could be next second, but in my analysis, I use the next minute. So I take average price of next minute after the news and compare it to the price of not this day, but next day close. And that presumes the model of trading associated with that would be that I send TWAP order for the broker, and he will give me the average price for next minute. That's a practical way of implementing that strategy. So that is something which you not just could measure, but you could also realize in your trading. That would be basically your return if you act on the news and close and sell at the next day close. Now, RavenPack produces normalized signal R, which will be first variable in my mutual information, and we use 10 years or less. My data analysis was done this summer. It ended with end of April, so don't have the results of the analysis until today. I'm analyzing them now, but maybe at next conference I will present it. So we measure the mutual information with only 5 probability bins, and the weight with some weight of stock significance. Let me say something about that. 5 bins, well, I would definitely prefer 100, but 5 bins turns out to be enough because you can still divide into 5 bins the number of events you have during those 10 years. If you would divide them in 100, for some stocks it would be too small statistics and I wouldn't believe it. So I had to compromise here between the mathematical rigor and practical availability of the data, so I compromised at 5 bins. I tried with larger number of bins, like up to 10, and the results were essentially the same. Now, weight of stock significance is more important thing. You see, the stocks die and get born. If you take Russell 3000 or Russell 2000 today and go back in time, you're cheating, because Enron is not there, but it was. If you would be trading, I don't know, 10 years ago, you would include Enron. So you should be using Russell 2000 every day of the past. What was Russell 2000 at that time, if you would want to do that? Instead of that, you could actually use the whole opened universe of stocks changing every day, and just find some invariant way of weighing those stocks. In other words, stocks which live longer, which has more volume, are weighed more. But you don't exclude anything from the past data, and you include all the stocks which were alive at that day. And as a weight, I use the integral dollar volume for the last month, to be actually, dollar volume is something not invariant. For a mathematician, it's disgusting. So I use ranking. In other words, at every day, stocks are ranked according to their volume, and this rank is invariant characteristics of the stock. It's not measured in dollars. It's just a number from 0 to 1, or from 1 to whatever. So we use that ranking as measure of the importance of stocks, because I want to pull together all the data and average it with certain weights, and that will produce me mutual information. So that's what I'm describing here. Rank is the position in the sorted list, and divided by number of stocks. That's a way of the weight of the particular stock in my average mutual information. So, for example, QQQ gets weight close to 1, and SPY and Google and dead stocks like one of my previous companies called Viewpoint would be very close to 0. So we included all the signals except the ones which are already backfitted. Among RavenPack signals there are original raw signals like ESS, etc. And then there are some composite signals which are like processed food, and I don't eat processed food. So I took only raw signals because they have no backfitting. Those which are processed already knew the data, and that's no. So here are my results. I found out, and here are all the signals, and that's mutual information. And to give you an idea, the maximal mutual information for 5 bins is log 5 base 2, which is 2.3. So these are huge data, huge numbers. For example, that's like almost half of the maximum possible. I don't give you the data for the ordinary indicators like stock delta or other technical indicators, but they are way below. They are like maybe 50% of that, or they're less than 1, or in any event, those indicators as indicators for the subsequent one-day price move beat technical indicators, which is a very good news, because people in the industry, my competition, mostly use technical indicators. Not many people are yet using these, though some will maybe start. Anyway, I'm very excited about this information, and I tip off my hat to RavenPack for producing that. And I also wanted to mention that here are some web indicators. And they also fare very well. They are different. They are not 100% correlated with the same indicators from the news. I added them also in my analysis, and I found out that they are equally strong, maybe even stronger, and that strength depends on time. In the past years, like 2007 to 10, to 110, it was less, 2010. But now they are equal, and web indicators are taking over. They are much more informative. The news are basically drying out. Everybody has the news. It's not so strong anymore, but web indicators are on the rise. Maybe I have even more here. No, that's it. So the conclusion of my talk is that indeed, if you measure the influence of the news and web indicators objectively, without ambiguities related to the Pearson analysis and all the other things, you find that indeed there is a lot of information there, and you could extract that. Now, you may ask, how do you extract that information? It's not these numbers you cannot plug into your program. And unfortunately, I cannot talk about that because that is my company's secret. But I can tell you only one thing, that there is a way to use this philosophy to provide automatic alphas which are inspired by this information analysis and which are strongly predictive. Thank you.
Do we have any questions for Sasha?
Looks like I scared everybody.
I have a question. I actually have a question. So you started looking at these raw signals, as you mentioned. Now, can you tell us a little bit more about what that means? What is a raw signal versus something more processed?
Well, a raw signal is something which was, thank you for that question, that I think is important. So the way you generate your normalized data, to my understanding, I asked that question to Peter and got an answer. So the way the raw signals, which are these signals, are produced are you have some experts which are making some tables, not looking into the price movements. They are making some tables based on their experience with the market. They are not retrofitting their tables to the price movements, because that's again no. That means you are cheating. So I hope, I rely on, and I would like to hear confirmation today that those normalized signals were produced in a universal way which is not related to the next day price movement. It's not like regression analysis. It's something which was done by experts based on their knowledge of the market, which of course involves the future, but in a very, very indirect way. It's not really related to immediate future of that signal. It is related to the whole history of the market for the last 10 years. And since the experts were doing that today and not at that time, there is a little bit of looking ahead, but very little. Now, that is raw signal, which I take. And that's similar to what I would get in future if I would be subscribing to RavenPack service, and I would be getting in real time the signals, and these signals will be processed based on the analysts' tables, and those analysts would only know the past. They wouldn't know how my price would move next day, because they have done the tables before. And that's acceptable. Now, what is not acceptable is composite signals. Composite signals, which are good to know, but you cannot use them. Because composite signals are produced by retrofitting the price movements to they take combination of signals with some coefficients, fit that to the data, and they fit it to the data from, I don't know, 2007 to 2013 or something like that, which means that now, from here to further, you can use them, because they don't know the future. Their retrofitting doesn't know the future. But if you are trying to make historical analysis, the backtesting of your strategy, and you would use the signals in a backtesting, that would mean that back in 2010, you would be using the composite signal which was fitted to the whole history. So you could not backtest and your strategy using those composite signals. That would be cheating.
So mutual information is going to pick up nonlinear relationships. When you look at the conditionals given your measurement on news, do you find the probability distribution has a linear behavior, bimodal? Do you see positive correlations between these indicators and the outcomes?
Thanks for that question. Nonlinear is really the key word here. I believe that the relation between the strength of the news and the future movement is strongly nonlinear. And every practitioner knows that because they threshold their signals. They say, oh, no, that's... So they manually threshold their signals, and I'm trying to avoid that. My mutual information tells you what you would possibly do if you threshold your signal in the best possible way. It doesn't say how, but if you do it. The relation is nonlinear, meaning that in this bin, like if you take the main bin, which is the Gaussian part of the distribution, basically there is zero. There is nothing. I mean, you should really eliminate that. Now, next bin is more important, and the bins which are too far to the fat tail maybe are interesting, but they're not very frequent, so you wouldn't make much money on them. So you have to do some nonlinear analysis of your signal. Yes, my recommendation is just forget about correlation, because correlation is dominated by the Gaussian noise. You have to use nonlinear. You should assume that signals are nonlinear and relations are nonlinear.
I have maybe a related question. What is the advantage of using mean MI as compared to, let's say, just regular stock sorting and top or bottom quantile difference?
Well, in this way, you detect the nonlinear effects, which might be very important, because all the standard statistical things, if I understood your question correctly, they put together in one number contribution from all the spectrum of all the probability distribution, and some of that is relevant, which is fat tails, and some of that is not, which is this random noise. So you want to filter out the random noise. And mutual information basically filters out the random noise. It weighs it with correct weight. Here is some question.
Just a very short question. Doing the mutual information, kind of looks like Shannon entropy, and just curious if there's other measures that you use for kind of, I guess, quantifying the mutual information. There's different kind of measures you can use.
Well, there is only one formula that I know for the mutual information, and the beauty of mathematics is that if there is no other way, there is no way around. If there is no, you could rewrite that formula, you could massage it, but it's the same essential formula.
Well, it is Shannon entropy, isn't it?
Yeah, it's Shannon entropy, right? There's generalizations of it. I'm just curious if, everyone uses Shannon entropy when you talk about kind of, entropy, but.
But these are all the same things. There are several subsets of, mutual information, entropy, as long as you have these invariant integrals. That's all. What is important is to use invariant ratios. Any parametric invariant formula for the mutual information or other quantities are related would do it. The mutual information differs from other things which are there in the definition of this information, because, like entropy, because that is normalized so it is 0 in case of independent events. What is important here is I want the quantity which is normalized so that it is 0 when events are totally independent, and it is always positive. So that's something which measures the mutual influence of events. So other definitions like entropy don't have that property. Mutual information is a particular combination of all these invariant things, which has the remarkable property of being always positive and being 0 only in case when events are independent.
Yeah, so just the simple question was, there's those properties that you actually wanted to identify, and did Shannon entropy just basically satisfy those in mutual information, or
you could use
the other way, like
no.
Start with Shannon entropy and you said,
It will be essentially the same. It will be essentially the same. From my point of view, any quantity you could invent which you have this property would do it.
Okay, so basically it's is it Shannon entropy just by itself, or it's just those properties that are important? And
Yes, because in many applied packages I found numerical procedures which are not correct, which don't have that property. Like if you just have the bins on the equal bins on the variable, that is, you destroy the property.
Thank you.
Okay, we have time for one more question.
So does the row new signal have fat tails as well? And this is the first question. And second question, are you saying that the main body of this row signal news distribution is noise?
No, I would say that this precaution about the fat tail mostly applies to those signals which are continuous, like delta price. Like, for example, if the price, if the volume is ratio of, like volume imbalance is small or delta price is small, it has almost no correlation, no relevance to the future price move. Only, big moves are interesting. Now, with news, I also found that the signal around 50, not far from the middle, is really mostly noise. Fat tails are like near 0 or near 100. So if you normalize signal property, like you subtract 50 and divide by 100, you have something between -1 and 1. So the middle, again, is sort of noisy. There are plenty of news which tell you nothing and people don't react. So yes, the strength of the signal indeed is important, and I think RavenPack did a good job of normalizing it, so indeed the tails are interesting there, as it was clear from their presentation also.
So in your technique, you're actually trying to find the tails in the price distribution, in the return distribution.
That's right.
Excellent.
Oh, no. In return distribution, oh yes. You mean my second variable, the return distribution, also is analyzed with mutual information. Therefore, again, mediocre returns are effectively suppressed.
Great. Sasha Migdal, everybody, thank you.